I used to love, as a kid, particularly the bits in the A-Team. They'd get captured by the bad guys, they'd get locked in a tool shed, there'd be a combine harvester, welding equipment, they'd come out with a tank and shooting watermelons or something, there'd be crazy stuff going on. So, at university, when I started to get into digital design and I started to hack stuff. You can move forwards. Do you want me to move forward? Okay, well. I have a microphone, it's all in the right place. We've got some feedback on this one. Okay.
Turn it off.
I've got a sore throat as well. Shouting's not going to go very far. So this is going to start feeding back pretty badly. Okay. Okay. All right. Where was I? I was at university. So, the A-Team was the big influence. I started to reuse stuff. I was a poor student. I didn't have the money to keep buying all these parts and stuff. So I started taking things apart and I started salvaging parts from them, then salvaging the devices themselves. And this philosophy stuck with me. I'd like to talk a bit about it today. I think it's a lot of fun to reuse devices and save them from the trash. More fun in some ways than buying new things. Now, there's a bit of a contentious thing. I'll come to that in a bit. So, I'll start with some philosophy of why I think it's a noble thing to do, and then we'll move on to some more technical stuff after that. So, I want to inspire more people to take things apart and to look inside devices that already exist. We seem to have a lot of people that are very interested in Arduinos and electronics, and this is great. These are things that you will buy and then make something out of. And I want to inspire people to then take existing stuff and take that apart as well. So, hacking something, you're making an object do something that you want it to do. It's often contrary to its original design. You'll often be making something into something that's not what it was originally meant to be. Non-technically, this could be moving a buttonhole, this could be putting a BMW spoiler on your Ford Escort. There's all sorts of examples of this. A lot of the things I think people create fall into some of these categories. So there's need for an invention, a fix. There's sometimes reuse by choice, if you're lucky, and sometimes reuse because that's all you've got around or all you can afford. And sometimes it's just to create something thought-provoking. It's for art, it's for fun, it's to make something beautiful. There are a lot of examples in the news. There's the Thailand floods. I love this stuff. There's the pictures of the cats and dogs with empty water bottles strapped to them. People salvaging stuff to try and save all of their stuff. There were the rebels in Libya making makeshift guns and weapons out of what they could salvage. So they had the need and they had to reuse stuff. They didn't have the supplies. Here's a great one from the Philippines. Bringing light to the inside of people's houses during the day can be very dark using just a water bottle stuck in the roof. So every culture's got a term for kludging or hacking stuff. In looking into this, Brazilians here will correct my pronunciation, this may be wrong. Gambiarra is the art of hacking stuff. It's the art of the kludge, the improvised fix, but there always seems to be a twist on the art side of it. So a lot of the gambiological hacks will solve a problem, they'll maybe just for art, but all of them involve reusing stuff, reusing parts and objects. Other hacks, retro appeal is a big one, where people are preserving an original design, reusing it for something. Cool vintage hardware, using it just because it's cool. Here's a hack by my friend Angus over here from our local hackerspace. It's in a Swiss piece of lab equipment. It's something that shows when our hackerspace is open and tweets. It's an internet-connected device, but it's reusing an awesome case. Kind of Dr. Strangelove sort of feel to it. By his inspiration, I made this out of an old slide projector. This is a digital slide projector with an old Nokia display and an AVR wired up to it. So it's kind of like a crappy 1950s sort of digital projector. But again, you're giving new life to these things which would otherwise just be unused or be maybe on a mantelpiece somewhere. Reusing them and you're appreciating the design and making it your own. So here's another example. I thought I'd do a little demo. Mine's a little bit simpler from the previous demos, but simple means reliable as well. I'd like to introduce Megaduck. Now I brought this along as an anti-heckling device. So it's kind of a force field coming out of here. We had a 110 decibel bike horn lying around the office. It was actually under someone's chair so that when he sat on it, it would... And we had a little squeaking duck thing. So a bit of araldite, wiring the sound output from the duck chip into the amplifier of the horn, and we've got this beauty. So this covers all three of those areas. Art and design, obviously it's the pinnacle there. There's a need, and it's reusing something. But electronics is really what I want to talk about. So I'm a bit worried that as a society we're going from 1940s radio and TV owners who would know how their devices worked, and if they broke, they would take the lid off and tinker with them, to mostly passive consumers. Obviously, we're a slightly different crowd, and we're interested in electronics and Arduinos and building things ourselves. But as a society, I really want to promote this idea of taking stuff apart and looking inside, because a lot of things, that's the only way you'll learn them. It's a very accessible way of learning things as well. I want people to start tinkering with stuff. So I'm worried these skills will fade. So this is my motivation for giving this talk. I want people to either yourselves take stuff apart and learn things, or crucially, teach other people to do these things as well. Does this look familiar to anyone? This was a small part of my junk shelf. I've got, I think I counted 3 other boxes, and there's a couple in the cupboard, cobwebs I haven't been near in a long time. We all collect all this stuff, upgrade our phones, and I'm as much a gadget freak as anyone else. Geeks love their technology, and these days it's designed to be old 6 months ago. You know, things go obsolete so quickly. We've got a lot of this stuff lying around, and this is also another motivator. There's all this raw material, things that can be used for stuff. So one of the reasons is to save resources. Part of this slide was also sort of trying to motivate people to not be as much in sort of the consumer cycle, buying stuff and consuming and buying stuff. I want to point out to the Freetronics guys as well, because this sounds like I'm about to go, don't ever buy Arduinos, and this is not the point. I want to highlight to people that obviously we work in a very a resource-intensive industry. So the computer industry is resource-intensive for making chips and that sort of stuff. So it's a balance as everything. So the reality is always somewhere between these things, and I'm just presenting an alternate view. Reusing stuff is one answer. So something to think about. But even recycling is not great. So if you have a device and you don't want it anymore, obviously putting it in the bin is going to add your heavy metals and your chemicals from your device to the ground. Recycling electronics is not a very clean art. We've seen photos of all this stuff going on in third world countries and people boiling things down and it leaching into the rivers. It's a dirty thing. So reusing stuff is much better than recycling it as well. I mentioned as a student I didn't have any money, so I started out doing this sort of stuff to save money. But it's also a bit of a cruel challenge, I think, in some ways. What's the best thing that you can make for free or for $1 or something? Arduino's, yeah, see, I'm trying not to sound down on the Arduino. I think it's a very, very cool platform. It's not that expensive, and that will be people's argument. Okay, well, it's easy to use, and so my slide here, try and do it for free. Oh, it's only $30, and we've all got them for free in our bags. I think they are quite expensive. If you start using them as a raw material, they're 30 bucks-ish. Then you build it into something. Then you need another one to develop your next project, so you buy another one. So this is cool for some things, and please do support the companies that are building nice bits of open hardware. But think about whether you can also reuse stuff as well. And it's a judgment call for you all. The education side of taking things apart, I covered a bit before, but this is a really big deal. You'll learn some really good design techniques. I always have a look at circuit boards and I'm like, oh, why are those two traces close together? Or why are those curved and those not? And there are all sorts of questions that you can ask yourself from looking at these things and learning by example. Building stuff teaches you stuff. Taking things apart teaches you stuff. Taking things apart and building stuff from that will be the best of both worlds and teach you some more. The other thing is taking stuff apart and learning how they work is very important for the robot apocalypse, which is, I'm sorry to say, coming very soon. The Terminator, he was taken apart, he was reprogrammed to go back and find John Connor and protect him. How do you think they got those skills? This was taking stuff apart, examining, right? It's very, very important. So this is a big deal. Big motivator for me. Difficult stuff is fun. This is the intellectual challenge. This is the hacker ethic. We like getting started with stuff that has the directions, and documentation is a wonderful thing. One of the real strengths of the Arduino, and the thing that makes it very valuable, is that there are lots of tutorials. It's a great thing to buy to start getting into electronics, to get into microcontrollers. Lots of tutorials and lots of documentation. Once you get to that point, it might be slightly more interesting, and I'm hoping there'll be a lot of people at this point where they've done the basic tutorials and those sorts of things. To make things hard for yourself on purpose, make things more difficult for fun. So this is an end in itself for me. I've done a lot of projects that are not very straightforward and very circuitous to actually build a blur widget, but that's not the point of them. The end is not the point of those particular projects. But stupid stuff's fun as well, so bear that in mind. It doesn't all have to be crazy reverse engineering and stuff. I'll demonstrate it again. Does anyone want to be blown out of their seat? But we've got a lot of stuff around, right? So 6 months ago, all of our things that we bought then are now obsolete, and we upgrade, and we like our gadgets, and everything's getting smarter as well. So our TVs, our printers, our scanners, all of these things are now computer-based. That makes them easier to hack in a lot of ways. They all run code and software. It's a lot easier to examine and tinker with. So I'd like to, as I said, inspire people to just have a go at this. It's not maybe as hard as it looks, and to give stuff a go is the first step. I work for a big multinational corporation, so I should probably say I'm trying to make it clear I don't want people to go out and break copyright and start ripping off bits of people's firmware and reverse engineer things ethically and legally, and please don't break the law. So I have to get that thing in there. Some devices are easy to hack, some are not. It's a judgment call, basically, choosing which is which. Your PlayStations or your iPhones are on one end. They're quite heavily locked down. It'll be in this category. There is a lot of effort gone into making these things unhackable. Now, there's a lot of smart people working on running code on your PlayStation or on your iPhone, or your cryptographic bootloader breaking and things. So I'm not going to talk too much about this stuff. Other categories, sometimes it's difficult to hack stuff just because of the way it's made. Very, very cheap manufacturing methods are one example. It's just out of obscurity. They haven't put any effort into hiding this chip. It's just that this is the cheapest way to mount a chip. You buy the bare die, you glue it down, and you stick something on top of it. But you can't see what the chip is, and you can't get at its connections. There are other quite mundane legal reasons. People don't want to document stuff because they fear, oh, we'll have to hire an IP lawyer and all that sort of stuff. And these are other ways that a lot of hints are hidden from us, the hacker. But saving money and developing stuff very cheaply sometimes makes things easier to hack. Corners are cut, and things are rushed to market, and the time part, crucially, is what makes things easier. So I call this open by cheapness. So you'll not design your own chips. You'll buy SoCs, system on chips, from some manufacturer. They'll probably document them, if you're lucky. You won't use custom ASICs, which take a long time to develop. Also, if you make 5 designs of something, 5 devices that are all similar, you'll actually probably make one design, one per circuit board, and then mount different components for different variations of the product. So this means you'll have lots of component spaces or footprints that are empty that you can wire stuff onto, or unused ports inside, which might be useful. Sometimes software does this as well. You might have a line of products with a single operating system that's common to all of them. So your particular product might have features that are easily unlockable or use a common code base, because it takes more time to develop 5 different forks of things. And another reason is that you'll have reference designs. The system on chip manufacturer will say, here's a development board. If you want to develop stuff with our chips, and please do, you can borrow the design, you can license it from us, or you can have it. So a lot of devices will be actually very similar to the reference design, the development board, which you might be able to download the schematics of. And some products are well documented on purpose. They're open, they're designed to be hacked. I'm thinking of the Open Moco phone. There's a couple of toys. The Robo Sapien springs to mind. They documented a lot of little bits inside that you could solder stuff onto. The Chumby I'm going to mention later on. I don't know if anyone's heard of that. Okay, cool little internet device, touchscreen sort of stuff. I'll talk about that a bit later. Things to look for. So reference design similarities. Sometimes debug code is even left in when you've got your common code base. People don't sometimes take the time to trim things down and do a proper release build. It takes time to do that, and you can get things to market maybe a month sooner or something if you do that. We've covered the unused test points, but the factory test ports are a very useful thing as well. So you have a device that's made in the factory. A test machine will usually come down and see if it's dead before you send it out the door, and that test machine needs to talk to the system on chip. The system on chip will normally be running its own test code, run through its self-exercise routines. So the test machine needs to be able to connect to this to drive all these things. And the easiest way to do this is usually the serial port. It's very, very cheap still. It's 2 pins. It doesn't need any particular connectors. It's not high-speed sort of thing, so you don't need a special circuit board design. This interface is also used by technicians when things go back to the factory. Excuse me. And they're everywhere. So my CD player has one. Got one in the back of a LCD monitor, back of a set-top box. This is on a PCI SAS card. It's got an ARM microcontroller and some flash and some RAM and a serial port at the top on a PCI card. This is a printer someone brought into work. I've got a broken printer. Do you want it? Okay. Let's see what we can reuse out of it. So 5 minutes later, I have the lid off, and there's a space here. So as good hackers, we should be suspicious of anything that's not used in the final product. Especially also, this projector's kind of poor, but there are 2 resistors mounted here. Resistors cost money. So no one's going to put these resistors on there if it's genuinely unused in this product. So something has at one point probably plugged onto this, and it's test port. So 3 or 4 pins, have a look out for these things, ground, send, receive, and sometimes power. You'd be surprised what's listening on them. So I connect up a serial cable to this on this printer, just took the lid off and plugged it on, and it's running VxWorks, and it's got a little shell on there, and it's got all sorts of debug stuff and little flags that you can tweak. So if you don't already have a USB or a serial to TTL or logic level cable, some of the people in the Arduino MiniConf, I think, got them, 5-volt ones, then get one of these. They're really useful. Be careful of the voltages when you connect things up. Sometimes you're sending 5 volts in, or 5 volts and 3.3 are the common ones, but make sure things won't go up in smoke when you connect them in. I had a USB to serial cable, and in keeping with the reuse theme, I just had one of these lying around. So USB to serial, and then serial to RS-232 to boost the voltages. So you can cut that chip out and solder on some wires and make one of these. So I saved, what, $3 or $4, and I reused something, just as a useful thing to have around. So there'll be JTAG. JTAG's a whole other situation altogether that I could talk about that for a while, but you can use it for PCB tests, you can use it to debug CPU cores in your SoC. It's another thing that can be very useful if you've got the facilities and the software. In-system programming ports, there's one of these on the Arduino. There's one of these in the coffee machine in our office. This is how, when you build a thing, you'll stick down blank chips and often just stick the firmware in on the assembly line instead of programming the chips separate. So let's look at one example. Household random digital device I had lying around. It was a lovely digital picture frame. I'm not well into these sorts of things. I like actual physical prints. But I had this lying around, and it was an upmarket one for the time. It had a high-res screen, USB, and does video playback and all that sort of thing. I thought, well, not bad for free. What's inside it? The first thing we noticed on this very, very dark thing that we probably can't see, it's got 3 chips, and there's one in the middle. System on chip, this is your processor that's got your controllers for your RAM and flash. It's got USB and video and all that sort of stuff on it. First problem, which you'll almost definitely run into if you take apart a random thing, is you Google the chip number, and there are 100,000 results, and they're all to buy or sell it, and none of them are, here are the interesting register definitions. There's no programming information for this. I searched for quite a while and couldn't find any. So I found a marketing leaflet that was all the information I could find. It's a very cheap system on chip designed for digital cameras and media players and that sort of thing. It's got an embedded processor. It's 100 megahertz MIPS, so it's a 32-bit machine. It's not too bad. It could be something useful that we could do with it. It's also got 32 megs of RAM, and that's enough to do something interesting with as well. MPEG-4 hardware and that sort of exotic stuff. So I kind of want to run code on it, but how? So here's the picture of the back. Again, some unpopulated pads. I think this was derived from a reference design. This is an example of one of those products. There's a little strip connector up there, which I think is designed for a camera sensor. And I think this is derived from a development board for this chip, which is designed for digital cameras. And they basically left in some of those things. One of the things that is in, see on this side, we've got a lovely gold pin header. And again, especially lovely gold ones, these things cost money. This isn't going to be fitted if it's genuinely unused, even though it's hidden inside there. It's not an end user port. So I think this is a factory test port. So what's on it? Maybe there's a serial port. Maybe look a bit closer. So there's a bunch of pins. We want to find 2 of them. They will be our serial port. The easiest thing to do is, perhaps as a guess, if you reboot the device, it spits out something like the D message when it comes out, when it boots. So if you've got an oscilloscope, it's quite easy. You can basically reboot the device over and over and have a look and see if you get a serial pattern coming out. If you don't have one, then you can even trial and error it. You can connect ground, and you can connect the input of your serial cable, try all the pins all at once, keep resetting it. And actually, before I had an oscilloscope, that's what I did on this exact device. And it does have a serial port. I'll show you in a second. The input, here's a little trick. You can sometimes differentiate a digital output and a digital input by the voltage. So a digital output will be driven by FETs up, say it's pulled up in this case, and it will be very close to your 3.3 rail, so 3.29 volts. Your input will be quite weakly pulled up, and sometimes you can actually detect that. You can guess that it's an input because it might be 3.97 volts. It might be a few millivolts less, and sometimes you can test this. The other way, if you're trying to find a serial port input, once you've found the output, you can connect, again, trial and error your serial cable around. You can stick a resistor in series, so if you try to drive an output, you're not going to blow anything up. And then you can hit enter a few times or see if you get a response. That's how I found the input on this one. And it comes out with all sorts of debug. There's pages and pages of this stuff when it starts up. It thinks it's on an evaluation board. So, okay, that's my guess of the circuit board being a derivative of an evaluation board. It's meant for a digital camera. It's got all sorts of code in it for taking pictures and that sort of things, movies. It's even got a command line interface with help. So you can read and write the flash card, you can display video, you can display images, you can dump memory, you can poke stuff into memory. See the do command up there? You give that an address and it jumps to it. So there's how we can execute code on it. So it's got a useful command line with interesting things that you can play about with hidden inside. This seems a bit weird. Why would you put this in? Why would you bother? Well, it's not an effort to put it in. They didn't make the effort to take it out. This is debug code. There are all sorts of asserts flying past. There's all sorts of, oh, I'm in printf.c and this thing went wrong. It's rushed to market. It's a common code base from a camera system. They didn't bother to take any of that out or to hone it down just for this picture frame. And the debug code is also left in. So this can be really helpful. So I started disassembling the ROM of this as a 4 meg ROM, and that's a puzzle inside a puzzle. So we recurse here, and pop, push. And there were all sorts of statements like this which made disassembling it a little bit easier. So first thing I wanted to do was find the serial port, get some debug out, find the memory map, figure out where the GPU, where the MMIO registers were so that I could actually program the peripherals on this thing. So start early, and I found a message in the ROM that I saw was printed out when it first started up. That's going to be their equivalent of their early debug printf sort of thing, referencing that. So find that function. That starts playing with some MMIO registers, and sure enough, that's the UART. So I've got my debug output there. And by doing that over and over, and by having a few interesting hours doing this, you can build up a profile of where all of the peripherals are and how to use them. One of the other things that is a good clue is that system on chips are very rarely completely new. They're very rarely completely redesigned. And sure enough, this chip has a slightly better documented earlier sibling. It's very, very old. It's an 8-bit chip, but it's still got some of the same peripherals. So they haven't reinvented the interrupt controller, and they haven't reinvented the UART. And it turned out that the SD controller, once I got some information on how this is working, matched quite closely to what I was seeing in the disassembly. So now I have some information on how to drive the SC port. So the other peripherals are that same sort of thing.
What did you use for the disassembly?
Obj dump and Emacs and painful stuff. So this is, I'll answer this afterwards, but that's a very good question. I'll come back to that, remind me. Okay, so this is just an example of something that's, so the design for cheap saves the day. Lots of information is left in, and also lots of debug ports and things like that, so it can make it a bit easier. So I just made an artful thing. I've got my sort of hello world thing there. Currently all it's doing is doing a Rotzune 90s demo effect sort of thing on the screen. I figured out how to mess around with the TFT controller. The interesting thing is this frame buffer is actually, it's not an RGB frame buffer, it's a YUV frame buffer, which sort of fits if you think about the digital camera JPEG display element of it. So all this stuff's going on the luminance channel, and then there's a separate chrominance channel which is adding the blue tinge there. And it's not very useful. It sits there and twirls and looks pretty. There are other things that could be done with it, like it could be a display device for a NAS or user imagination. But so that's an example of one thing. Something more useful and less arty. I had a need for a bit of bench equipment. I mentioned JTAG earlier. I had a board that I wanted to program using JTAG, and I didn't have the equipment to do it, so I built it. One of the things that I used was, these are some of my favorite class of devices. It's the trusty ADSL modem and Wi-Fi box. And these things are great. They're plentiful. They're crappy. All the firmware is always terrible, so people always upgrade them and throw them out. So there's lots of these around. While I was writing these slides over Christmas, my hosts said, oh, I've got these lying around. Are they any use to you? So these are the two here, and they both run Linux. As a lot of people know, a lot of these things run Linux from the factory. There's also OpenWRT and DDWRT replacement firmwares for these. A lot of the projects I've seen with OpenWRT, a lot of people seem to use them for configuring their firewall better or running BitTorrent clients on the routers. In Australia, the word's pronounced differently. One's a rude word and one isn't. But these are all software things. So a lot of the OpenWRT things are software-based, and there's more to them than that. There's hardware as well. So they're often MIPS-based, Texas Instruments and Broadcom and so forth, a few common chipsets that run these. And I love OpenWRT. I've used it for a whole bunch of projects. It's very, very cool. For those that haven't used OpenWRT, It's a bit like BuildRoot, which was a project to build you cross-compilers and a kernel and a UC-libc BusyBox and a root file system for a device. It's also got something which looks a bit like the ports tree in BSD. So a whole load of make files for all sorts of software. It will go off and download and patch and make you packages for these things. So these devices are great because they're fairly capable. They're 150 or 300 megahertz, that sort of end of things, 8 or 16 megs of RAM, 32 if you're lucky. It doesn't sound like a lot, 8 megs of RAM for a Linux system. If you haven't used UC-libc, it's tiny, BusyBox, very, very small. You end up with a lot of memory, and you can actually write some cool code in that space. But the coolest thing about these things is that they run Linux. They're a very familiar dev environment. You can run Perl on them. You can write stuff in Python, C, Erlang. Well, I'm not sure about Erlang, actually. 8 megs? I don't know. You might be dreaming. OK. You can use Lua. You can use Ruby if you're a deviant. There's all sorts of stuff, but they're great. They will have USB hosts sometimes, PCI sometimes, GPIO pins that you can blink on and off. Fair bit of RAM if you think about that. So the 8 megs, you might have 6 megs free compared to a microcontroller and an AVR. That's tons. Wi-Fi, Ethernet, and so forth. So there's cool stuff you can do with them. You can go and Google some of these things. I think I've got a link for the espresso machine thing at the end. Someone's made a PID controller for the heater of their espresso machine, and it will, I don't know, tweet how strong your coffee is or something. But there's all sorts of other things, streaming music systems. They've used the USB host of one of these things to do some USB audio. They've used the GPIO pins to have buttons or drive LCDs and put them in a nice case and that sort of thing. My favorite is this radio-controlled car thing. They'll get an old Wi-Fi box. I've seen a few people do this. You have a camera on top of the USB host, you're streaming JPEGs back to your laptop, and then the control system back out, you've got GPIO pins to drive stuff around. And it's good fun. I have this on my list of things to do. So I mentioned the JTAG need. I had the need to make something. I had one of these lying around. It has 8 megs of RAM, 150 megahertz processor, so it's well quick enough to run my software. And what I did was hacked my old parallel port JTAG lead into the GPIO pins of this box. I didn't have a parallel port on my PC anymore. I got rid of my last PC with a parallel port a few years ago. So I had all the software ready. All the software does is, on the parallel port, it looks like an I/O port. So it bit bangs the JTAG stuff through the parallel port. I did the same with the GPIO pins. So all I needed to do was take this apart and find some GPIO pins to use and get the software running on it. The kernel was a little bit broken on this one. They're all sort of very common chipsets. Often any random box will have a chipset that's supported in another configuration. So even if it doesn't work out of the box and is a little bit broken, it's usually a tiny bit of configuration to get it going. These chips have got 2 Ethernet ports, for example, and they were swapped around on the one port on this, so I had to reconfigure that. So inside, there's the board. I don't know if you can see up the top, there's some LEDs for the front panel. There are also some empty spaces there. This is an example of designing stuff cheaply by making, you can see the label down the side, 6 products with 1 board. For the different products, you'll differentiate them by fitting different features. So the spaces for the LEDs at the top, they're just for other more insanely cool products that this one isn't. So the other thing I could tell from the kernel source, which is available, thankfully, although it's a bit of an uphill battle with some of the vendors, but the LEDs at the top, they're driven using the GPIO framework in the kernel. So I know they're GPIO pins there. They're blinked on and off in software for network, heartbeat, that sort of thing. So it stands to reason that the empty spaces are also GPIO pins. So cool, I can use those. I just need to know which is which, so we need to map them out. My plan was to set the input register. There's a single 32-bit register for 32-bit I/O pins. Set them all to an input. Hack the kernel so it doesn't mess around with them while I'm looking, and then keep reading the input register over and over while I poke about on the board just to try to beat them out. I use this amazing piece of technology here. This is a clip with a resistor on the end. So you can clip to ground or clip to power, and you can pull up or pull down random pins while it's running. Watching the input register, you see which bits change, and you can go around and do that. But you don't even need to write a kernel driver to do this. Although these are obviously privileged registers, and these are in your physical address space somewhere that userland can't get to them, you can just, now, before you look at this, this is not a good way to code. I'm not suggesting making embedded things like this, but you can open devmem, you can mmap it, you can present a page of physical address space in your user process. The page that has the GPIO pins in it, you can poke that and you can set the direction and then you can just read it over and over. So do this, go round. There are lots and lots of empty spaces on this board, as I showed before, and I made a mapping up. I found 12 of the I/O pins by doing this. It's very quick to do this. And I found 12, so I needed 5 for my project. And you can drive serial LCDs, or you can put SD cards on, or there's all sorts of other cool things that you can do with these. And then ultimately my project was that buffer chip, some spaghetti wiring, and soldered onto some of the pins that I pictured in the previous slide. So this hack cost 50 cents for that chip, and now I have a useful thing for my bench. I do have a note here to just overemphasize, please don't poke things around in DevMem for an actual product, but for a random hack, it's all right. Everything I've talked about so far has been a bit of reverse engineering here and there, an undocumented system, and trying to find out how to use it. So compare and contrast this against another project. This one is open by design. It's an Insignia Infocast. So this is made by Chumby, or designed by Chumby, but made by Insignia. This is available in Best Buy in the States, or was when we were over there a year and a half ago. So it's sold, it's a popular consumer electronics-oriented thing. It's got a touch screen, it runs Flash applets, you give your Twitter stream, or you can have streaming audio, that sort of thing through it. Chumby's initial version was a smaller touchscreen-based thing. It had a cuddly exterior. It was designed to be hacked. It was designed to have things sewn onto it. It was bedazzled, painted. The inside's also designed to be hacked, so it's an open design. The PCB, the schematics, the firmware, everything's available. There's a wiki on their site. There's no trying to find cross-compilers. They'll give you cross-compilers. They'll say, here are the pins that do this. There's even a hack port inside with clearly labeled GPIO pins that you can wire things onto. It's very much a consumer product, but it's designed to be hacked, and I like this combination. So I bought one of these a year and a half ago. Jen here said to me, going on and on and on, oh, it's so hackable, it's wonderful, it's great, I like this company. She said, also, why haven't you done anything with it? Why haven't you hacked it? So a challenge. I thought, okay, I'll do something. So I plan to have it here and demo. What I've made is an internet-controlled cat feeder. I'm actually just going to show, I'm just going to show a video because it took me hours to get the cat into the luggage, and it was, you could tell it was going to end in tears, and it just seemed like a bad idea, you know? So I don't know, maybe next time, but some sort of training thing. So I made this with, let's see if I can actually Alt-tab to it. Oh, okay. And then that way, yeah, okay. There's a lot faulty about him. There's a lot faulty. Okay, so it's a remote control cat feed. It's made out of chopsticks and a yogurt pot and a servo motor and I think tin beans? No, they're tin tomatoes. So there you go. That moves out and then the cat food will drop out. I'm told it will also work on toddlers. This might be a good idea if you go away for the weekend. So as you can see, we're controlling it here. So there's the customer there. Like his ears, he's like, oh my God, something's gone on. So, and it goes back to its original position. So, okay, so it's obviously a pretty crazy piece of technology there. Yeah, I didn't say it was without drawbacks. There are issues. So there it is, a bit of a close-up. Some closed pegs too, I forgot to mention them. So, and this was easy. This took about an hour to do, including software. The kernel source was available. The schematics were available. The PCB layout was available. Also, Chumby are a good company in this sense as well. They chose a SOC vendor that actually released the datasheet, and it's not under NDA. So you can download the datasheet and say, oh, okay, I want to use that pin. For this, I wanted to use the PWM pin. So for those that haven't used servo motors, you give it a 1 to 2 millisecond pulse every 20 milliseconds, and that dictates where it points. So a PWM pin is ideal for this because you can program them to give a pulse width. PCB's even got labels, so okay, I'll start looking around here. Here's the serial port. There's no guessing which pins are which, measuring all of that, that's labeled. There's JTAG, there's a hack port. The GPIO pins, don't have to guess which numbers they are, they're actually numbered. Even says, please don't get more than 50 milliamps from here. Very, very friendly for the hacker. So tracing this, I tried to find which one of these pins was my PWM pin, and it wasn't there, they haven't brought it out to there. But because the schematics in the board layout are available, it's on this pin. It's on this resistor. Just find this resistor and solder it on. So that's all the hack is. It's 3 wires and 1 thing there. And it's only this simple because they were very kind and they released all of this information. So this is a bit of a contrast. So we love poking around in DevMem. So I wrote a little utility which takes an address and a thing. A little bit of shell script there to set up the registers. Could have used Perl, I suppose, or something. Python? I don't know. Anyway, so you set up the registers, the pin mux is the width of the pulse, the duration of the period of the pulse, and the width of the pulse is just this final register. So this, as I said, was in the shell script. So stick these into a CGI script, run them on the HTTPD, which comes with the machine, and that's it. So little hack there. Some other things which I haven't properly, I'm not going to properly go through them because they're not really finished, but other examples of reuse. This is very dark, isn't it? So this is an old laptop panel, really nice glossy laptop panel from a Vio, and I had it lying around. There's a broken machine somewhere. Can't see any of this, can we? This is a Beagle board, believe it or not, nice red thing. Then there's a little attached board which I made in the kitchen. So the Beagle board outputs RGB, well actually by this version only outputs DVI. The chip itself will output 24-bit parallel data for video. So I took the, took the DVI chip off, wired on a whole load of little wires, I think we can sort of see that, which will take stuff over, get some good optics for this sort of thing, and, or see an eye doctor. This is it's not good for your eyesight, so magnify it. Anyway, so take it off, turn it into LVDS, which is the standard that it's a very high-speed data standard which is used to transmit data to a lot of flat panel displays, and then send it out. That's the socket for the laptop panel. And made a little arty useless thing to hang on the wall. The software for this is just showing a test picture. I've got some basic GL stuff going on it, and the Beagle board's kind of cool. It's got a 3D accelerator and those sorts of things. So it's reusing something that was lying around, and I have to admit the Beagle board was lying around until I did this as well. I got it and then got disinterested like any good geek. So got something else and got distracted, but that resurrected my interest for that and created a little arty sort of thing.
Did you leave in the debug code? Because I'd like to hack it.
More than that, yeah. As you guys find it in DevMem somewhere, it's around there. Here's a bit of a horrible example. So this really was I got this some weird stuff in California, which is a great source for surplus parts and prototypes for things. This was a prototype board from Intel. I have no idea what it did. It's some sort of telephony switchy thing. It had a chip there, and it had a chip there, and a few other bits. So this is sort of how it started out, and I bought it for $4 on a Sunday morning. But it's got an FPGA on it, and as was mentioned in some of the previous talks, FPGAs are very cool. You can reprogram them to do all sorts of things, but they're also really good if you've got a board and you don't know the connections to it. Well, they're malleable. You can program what the connections are. So as long as you find them as inputs, and this is what I did with this, using the wire and the clip and some JTAG software, I set all the pins to inputs and probed around on the board. So I found a lot, maybe over 100 pins this way. And because they're malleable and you can program them, you can do what you want with them as outputs. And you can do fairly high-speed things. I had an old TFT monitor, desktop sort of thing lying around. The controller board was all broken, except for the two fuzzy chips over there in the background. I can't remember whether it was a hacksaw or a circular saw, but I chopped out that bit of the PCB and kind of wedged it on there. And again, lots of little fly wires. So this is taking the parallel video data in the same way as the Beagle board hack, and sending it into the LVDS serializers and then off to the panel. So it's a very nice panel. It's 1280, 1024, full color. Here's a little RAM chip that I added to it for a frame buffer to store video data, and a trusty Game Boy Advance, which again was reused. I haven't played on it for about 10 years at that point. So at the moment, it scales up the video and displays it on a big, this is just rested that way. It's convenient because of the way the wires are, so it's actually meant to be that way around. But if you rotate the images, the lighting goes all funny and your brain hurts.
But the lighting's meant to be all funny and your brain hurts when it's a GBA.
Yeah, well, this is, yeah. And now it's a nice backlit screen. I've spoiled half the fun of playing with the GBA and trying to tilt it. But. So that's all it does at the moment. One of my plans for this is to, I'm making a BBC Micro, which is a little English computer from the 80s. And this is kind of partly done. So it's not well enough to demo at the moment, but maybe in the future. So I'll start wrapping up. I'm going to reiterate this again. Please just give stuff a go. Take stuff apart. See what you can find. There's all sorts of stuff hidden away in these machines. We all buy stuff, and it's kind of part of how society is. If you do buy a new thing, at least think about the thing that you've left behind, and do something with that as well. Give it a bit of new life. Tell the world about it. Write it up. Put it on your blog so I can read it over coffee. I like this sort of stuff. Hackerspace is a great place for this. There are the tools, but there are the people. This is the important thing. Sharing all this knowledge is pretty cool. And support the companies that build open software. It's a great way to learn new things. So this is my call to arms. Don't just passively leave these things aside. Do something with them. Disassemble them and learn and create from them. So thank you and questions. These are a few fairly random links. There's the Brazilian stuff, some of my projects, and Hackaday. I like Hackaday. It's a great blog with all sorts of things which are usually reuse based, 5 or 10 a day that you can read in the morning. So I'm done. Thank you. Thank you.
All right, where's our first question?
Down the front.
Yeah, can you answer the question about what you use for disassembly and so forth?
So I've heard that IDA Pro is very good, but it's very expensive, so I didn't go down that route. The thing that annoys me about, well, so obviously ObjDump can disassemble pretty much anything. Once you know the chip architecture is all you can guess. And I've disassembled a few things like that, and it's a really painful thing to get a few million lines of disassembly and then in Emacs go and edit it and put labels in and that sort of thing. So a project I've half started on about 3 times when I've been doing this, it's getting really annoyed and going, right, I'm going to write a proper disassembler that will also be able to reassemble and that sort of thing. One of the things I'd like to see would also be start scanning here and go through and actually interpret the code that you're disassembling, because then a lot of the constants, so for example on MIPS, you'll load 32 bits, you'll load an upper 16 and a lower 16. And a lot of the disassemblers will just treat those as separate values. What I'd like to see is the code actually executed, and for it to go, oh, that's B00115, that's the UART receive register, and actually put those things together. So,
Please continue on that project.
yeah, I wonder whether we should try and get something going on that. Yeah, that'd be fun.
I noticed you roll your own serial cable. I guess you had spare parts. Do you use a bus pirate, or do you always just roll your own gear when you need it?
I've only got one serial cable and I don't blow it up. That was my solution. But someone's lent me a bus pirate and they look really cool. I haven't used one yet. But yeah, they look like good little devices. Hello?
I've got a question about the chips with the blob of stuff on top of it. Have you found a reliable way of getting that off?
I haven't personally done that. I've seen things on the net, people using nitric acid and hot nitric acid to do that sort of stuff. But it's something that I'd like to see someone else do, and maybe I'll stay away from burning a hole in our sink in the kitchen and stuff.
So one of the challenges in hacking things is that in a number of places that the cheap manufacturing and differentiating products by code is to my experience makes things more difficult to hack because they're less examinable. And you just said the opposite, so I just thought.
So would you be wanting to take this differentiated product and turn it into the more expensive version? Is that the sort of hack, or do you mean completely reuse for something else? Because I agree with you in the first sense. There were a lot of things, like I remember in the early 90s, US Robotics did that with modems. They made one modem and had 3 different versions, and you could get twice the speed by changing the firmware and stuff. I haven't looked a lot into that, and I can imagine re-adding features that are taken out on purpose in code would obviously be very difficult unless you can hack down the firmware.
And it's just a product differentiation like strategy for marketing purposes. It's not really the
I wonder if that's done with products that are. I'm guessing here. This is pure speculation, but I wonder if that's done with fairly expensive products, fairly rigorously designed products from good companies, as it were. And what I was more talking about for the design by cheapness and the code left in were kind of the very, 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 very low cost, very, very no-name brands that you get on Deal Extreme and those sorts of things, which really are they're trying to be 50 cents cheaper than their competitor and stuff. And I wonder if you'd get more out of the Intels and the big companies of the world.
Yeah, hi mate. Hey, I'm just wondering what kind of JTAG tool chains you use.
OpenOCD is cool. They support a whole bunch of processors. I use something called Cable Server, which is so this was for the Xilinx system. So I was trying to program a Xilinx device, So Xilinx have got their own Windows and Linux proprietary stuff, which bit bangs the stuff through parallel port. One of the other things it can do is talk to one of Xilinx's proprietary boxes or another PC running their own cable server thing. And someone's reverse engineered the protocol and written an open source, a Linux-based open source application, which you can just run on any old Linux box with a parallel port and then point your proprietary Xilinx software to program. So it was that part that I'd have running on the ADSL box.
So what was your most frustrating experience with something you wanted to be able to hack and weren't able to, and what was it that stymied you?
How long have we got? All of it. All of it. I'll probably toe the party line in saying I'm most frustrated with some of the proprietary products that people, unfortunately like me, have bought. I'm an Apple owner, and I think this will be my last iPhone. I don't like the way it's already gone. And especially with some of the I/O stuff. Now, I've jailbroken my previous iPod Touch, and I have a little AVR plugged onto the bottom to do something broadly similar, not quite as cool as the USB links, but that's going to get harder and harder. And eventually, they are going to take. It's going to take a lot longer to jailbreak all the more modern things as all the holes get closed. So, yeah, it's an obvious answer, I'm afraid. But yeah, the proprietary nature of a lot of consumer electronics is the most annoying thing. This,
that's a sort of interesting point that I've kind of struggled with the whole reverse engineering thing. Is that reverse engineering is really fun, but at a certain point, if you're not sort of adapting for a sort of a current, so if you're not adapting for an old product, but you're adapting for a current product.
What do you mean adapting for?
Oh, well, as in, like, if you want to try and make it work in the way that you want it to. So,
okay.
Standard thing being...
like writing a driver for something.
Yeah, exactly.
Yeah, okay,
The kind of tricky thing is that it's fun to do, but in fact it encourages the very behaviour that we don't want, which is it's encouraging people to buy something that doesn't actually, be open out of the box.
Yeah.
Do you kind of ever struggle with that as a, hey, this is really cool, and I'm finding out how it works, but I don't actually want to encourage people to buy it because the company's making it difficult?
So I don't do a lot of that. I've never written a driver for a USB random camera that doesn't work and those sorts of things, unfortunately. Most of the stuff that I do is really just literally old crusty stuff that's lying around. So I'm not making a purchase of something in order to hack it, although I have done that, like the Chumby thing, the InfoCast. But yeah, so I can't. It's not quite the same thing, I think. So I'm trying to just take something that already exists. So I don't think it will be encouraging the company to do that because they're not getting a purchase out of me. I'm finding these things from people throwing them away and giving them to me and stuff. So,
although as you say, what you did buy because you knew it was open.
Because I knew it was open.
So that is actually encouraging that good behaviour. So.
Yeah, other way around. Yeah, you're right. But as I said before, I did also buy an Apple product, so kind of my karma points are way down there. So.
Could you please maybe talk a little bit more about your BeagleBoard thing with the LVDS panel and how you went about reverse engineering the pinout on the LVDS panel and what sort of hardware you're using to talk to the LVDS? Because it's certainly very easy and very cheap to get lots of discarded old broken laptops and stuff where you've got the LVDS panel, but it tends to be quite hard to actually hack that into something practical where you're talking to the LVDS.
Okay, so there are two things. So often the manufacturer will use a standard panel or 5 standard panels, but they'll all be physically the same and have the same connector. Then the manufacturer will use a completely random cable. So the connector on the motherboard is no one knows. The panels themselves are often documented, so that's actually very simple because you can, you've got 40 pins in a row and you can just beep them out and figure out what the connections are at the other end. Once you've got your LVDS pairs, it's all very standard between most panels. They'll either have 3+ clock or 4+ clock, depending on if they're 18-bit or 24-bit panels, how much data is being sent. And then the LVDS serializers are also fairly standard. Once you get one that's appropriate for your data width, you can sort of plug them on and then just present them with your 24 bits or 18 bits of pixel data and the clock. So it bears a lot of resemblance to other designs that are made in the same way, and you can, some open source things or open projects that you can look at. The backlight was the question. Is the backlight hard to figure out? Okay. The question was about reverse engineering the backlight and how to turn it on and off and dim it. The backlight's not as smart as you see from the software side, so all of that setup and I2C things here and GPIO, that's kind of done on the motherboard, it seems. So most laptops will have just power and an enable signal, and you PWM the enable signal going in. It's not a smart device that you're sending I2C transactions to. So that's fairly easy. You've got 12 volts ground, 5 volts, and something that's a square wave or fully on. And so that's relatively easy, but that's another thing, yes, another thing that you have to reverse engineer. So.
Okay, guys, I'm afraid we've run out of time, so I'd like to thank Matt for his talk. Thank you very much.
Thank you very much. Yes. Thank you. Thanks very much. Thanks.
And the Linux conference has handed him a memento of the occasion. It's nice and hot up the back there, I realise. We've asked the university to do something about the air conditioning. It is broken, it's supposed to be fixed, but we don't know when.